Doug Morris. I'm going to tee up the next forum, or next panel. We have assembled a team of experts to discuss BOP design requirements. The question for the panel is, what new design requirements are needed to provide assurance that BOPs will cut and seal effectively under foreseeable operating conditions? The moderator for the session is Richard Sears. Mr. Sears is well qualified to lead this discussion. He's a consulting professor at Stanford University, where he teaches courses in energy systems, technology, and economics. He led exploration and development projects for Royal Dutch Shell for more than 32 years before retiring in 2009. He served as a senior science and engineering advisor to the National Commission on the BP Deepwater Horizon. He is currently a member of DOI's Ocean Energy Safety Advisory Committee. He holds a bachelor's in physics and a master's in geophysics, both from Stanford University. Thank you. Richard, it's all yours.
This is going to be an important session to, I think, set a lot of the framework for the discussions on the day, and the panel that we have is really well qualified to do this. I'll introduce them as each gets up to speak. Just as an overall introductory comment, I thought the first panel did a great job of bringing us up on post-Macondo, what some of the key learnings were, what some of the revelations were when that accident happened. To me, one of the most important post-Macondo learnings from industry, regulators, all involved, is that the unthinkable actually could and did happen, and that the systems that were thought to be robust and reliable turned out not to be, on many levels, not just mechanical, but people as well. And so the BOP being an integral part, key part of this is an important place to focus for this day, and to look at these systems and how the BOPs can be better designed and work better in the future. The first speaker for this panel is Bryce Levett. Bryce is with DNV and will give us a nice overview on system safety and where the BOP is in that system. Bryce has 25 years experience in the oil and gas industry with a number of companies. His current position is Director of Risk Management Solutions for DNV North America, and works on risk management consulting for the oil and gas industry. So, Bryce?
Thank you, Richard. Good morning, everyone. To set the stage, I really want to talk in terms of barriers. And this is just a simple diagram to familiarize everyone else. And this is really to echo on what Director Watson had said when you talk about safety at all times. We need to think about this equipment being a barrier that needs to be there all the time, not just when an inspector comes out. So the way that we think of barriers, we have a hazard which can be present, which can escalate into a top event, if you will, which is at the center. And then on the left-hand side, there's a number of different causes which could cause that hazard to become the top event. However, there are barriers in place to eliminate that from happening. If the top event does occur, then you can continue to escalate into certain types of consequences. There could be a number of different consequences you could escalate into. And again, there are barriers in place to control just how bad those consequences get. In terms of talking about a BOP, we usually paint the picture, the hazard being that we have hydrocarbons in the formation. That's why we have BOPs. The threat is there. It could escalate to a loss of containment, which is what we saw when Macondo occurred. Threats could come in the form of shallow gas when the BOP isn't in place. It could come in the form of unexpected high pressures. But there are barriers in place to prevent that from turning into a top event, which becomes the loss of containment or a blowout. On the right-hand side, these events can escalate into a number of different things. You could have a gas release, you could have uncontrolled well flow, You could eventually have explosions, fire, loss of life, sinking of rigs, etc. Again, there are barriers specifically in place that are meant to stop that from escalating to that point after the event has occurred. In terms of talking about new regulations for BOPs, we think it's extremely important to understand what exactly are we talking about in a role for a BOP. In its traditional role, we look on the right-hand side and we think about primary well control being the mud, the cement, the drilling riser, the casing, etc. And then backing it up is the secondary well control, which we call the blowout preventer. It's always perceived as a secondary well control backup to a primary well control, which is the main means by which you prevent loss of containment. In this particular role, and this echoes a lot with what Dr. Hunter was saying in terms of its functionality, what are the requirements in this particular role? Well, for one thing, it has to be functional for the well conditions. So it has to be able to handle the pressure and the temperature and whatever you happen to have in the wellbore at the time, what kind of pipe, what size, diameter, etc. And how do you make sure that something like this works? Well, you have to have verification and testing, and a panel later on will be talking about that very subject. It has to work on demand. It sits there for a long time doing absolutely nothing for the most part, and that's kind of what you hope, that you never have to really use it, but when you need it to work on demand. That means that we have to have monitoring of it, give it a constant monitoring system. We know what its health is. We have to understand what state it's in. And again, Dr. Hunter was saying, the questions we couldn't answer. Is it closed? Is it open? Is it locked? We didn't know. We have to have a way of verifying what that state is. It has to be activated when needed. And this goes back to what Deputy Assistant Secretary Smith was saying. There's a person involved in all of this. And there are human elements to the use of this. And people have to know when to use this at the right time. And that includes being able to monitor the well much better so you know when is the right time to do this. And the Sperry Sun data, as you saw, was quite confusing. And then lastly, there has to be a continuous learning process on this as well, which means that we need to come up with a robust system by which we register not only the failures, which we've typically seen, we need to register the near misses, and we need to register the successes. When does this work? When we asked it to work. That was a success. Let's start a database on all of this, if you will, so we can collect this information and understand just exactly how successful are we with the use of BOPs. Now, if we then move over to the right-hand side of the bow tie, we can also talk about the BOP playing a role over there. So the top event has already occurred. Now we're expecting the BOP to act as a barrier to basically prevent escalation to a much larger unwanted consequence. But we would argue that this is no longer blowout prevention, because typically we talk about barriers on the left side as being preventative and on the right side as being mitigating. So we would argue that it is now called a blowout arrestor. It now has to stop or arrest the blowout, not prevent it. It's too late now, the blowout has occurred. Now you want it to take a completely different role. In this case, the requirements change. So again, we have pressure and temperature. We have the question, what's in the well? Now we have flow. Now we potentially have a well flowing through the BOP stack and the demands that it function there. But again, it's verification and testing that's needed to prove that this is what it's going to do. It still has to work on demand. There still has to be monitoring, a verification of state. Activation when needed. The question mark comes up on human elements. As we saw in Macondo, suddenly the human element goes away, especially when disaster takes place at the surface. You can no longer potentially rely on humans being there to intervene and use that BOP in that situation. So you have to consider that. And you have to start thinking about automated functions at this point as well. Really, what is needed to make this work if there are no human beings there to push a button and say activate it. And lastly, after action learning. And this is adding on to what we've already said in the previous, but what we're suggesting here is to start thinking about black box recording. And I think we all wish we had a black box on Macondo that we could have retrieved, where we could easily pull up and figure out what exactly happened, what buttons were pushed, all those sorts of things. So we need to start thinking about black box recording in terms of after action events have occurred. So to summarize what we're saying in terms of new requirements that are needed, you have to think of it in two separate roles. You have to think of it as a blowout preventer. You have to think of it as a blowout arrestor. This role needs to clearly be defined. You have to answer the question, where do we want this to sit in the bow tie in order to define the requirements? And then novel designs require functional specification, not prescription. And this is really echoing what Dr. Hunter said about define what, not how. You need to define what you want something to do, not how you expect it to do it. And we add further that given the fact that we're asking for this to be usable in all foreseeable operating conditions, let's define what that is. It has to be based upon a holistic risk assessment and asking the question, what are the foreseeable operating conditions in which this equipment has to function? And establish the performance. Don't restrict what the solution can be. Let the manufacturing companies and everyone else come up with a solution to meet that performance. And then we move on to control systems. And again, this is where Deputy Assistant Secretary Smith had said, it's about people interpreting things. This is very important when you think about how you design control systems. You have to consider what human beings are capable of interpreting in the decisions that they make. So therefore, we feel you have to establish what the potential human limitations are in this whole circumstance, and then start incorporating automatic functions. Don't go designing a control system before you realize what people are capable of doing. And it has to be able to address all of the conditions that are there, especially an automated system. It has to know what is the condition in the well, what is the condition of the equipment, what is the condition of all the inventories you have. If you require mud, do you have the mud? Has the mud disappeared? Will automated systems know that? Will they try to do things or not? And then a black box, again, to record all the important information, very similar to what the aviation industry has demanded in there. Design requirements, they will only set the minimums. They will not set the maximums. Designs can be much better than the minimums, and it should be set up in such a way that you allow for continuous improvement. The question becomes, what's the best available technology, what's the safest, and when should it be adopted? What sort of grandfathering do we have to think about? Because at the time of the Macondo well, there were solutions to shearing that covered the entire bore, but it just wasn't necessarily in place. And lastly, it should address its relationship to all these other barriers that we talk about.
The second speaker in this section is, this panel is Dr. Roger McCarthy. Roger has a long career in both this industry and others, and in the investigation and understanding of complex mechanical systems and their safe operation and design. Within the oil and gas industry, he's been involved in the investigation of several incidents, including the explosion and fire of Piper Alpha, the grounding of the Exxon Valdez, and many others. He's a independent consulting engineer, and was also a member of the committee for the National Academy of Engineering and the National Research Council investigating the Deepwater Horizon. So with that, I'd like to introduce Roger McCarthy.
Briefly, many of the speakers have touched on really the important points of this, and so I will just try and emphasize where I think some nuance is important. First, the new design requirement should at least address our past known failures. And I appreciate Director Watson's comment that we don't want to fight the last war, but remember, we lost the last war. So if we fight that war again, let's at least win that one. And we didn't win it last time. So at a minimum, we should be able to anticipate with our current design regulations and incorporate in them all the history we have paid so dearly for by not being prepared for the last disasters. And obviously, what we learned in the investigation of the Macondo well system, which many people have touched on, and Deputy Director Smith did an excellent job of going through, is obviously there were significant deficiencies in the design process of the BOP itself. And obviously, and most importantly, the BOP system was neither designed nor tested under the conditions it was going to encounter. And I thought Secretary Hayes hit it right on the head when he says it's got to cut and seal anything that's in front of it. But I would add a caveat to his remark and say it's got to cut and seal anything in front of it when all hell is breaking loose. And there is the tough part. And I think as Mr. Smith touched on earlier, these are very stressful conditions when you have a disaster, especially when you're trying to recapture a well. Obviously, because of the flaws in the particular blind shear rams, it was not able to shear a set of pipe that was in compression dramatically below its shearing capacity. And obviously, I love the term that Dr. Hunter used, shear certain, which I had not heard before, but I will remember that one. And you note in quotes I put under the most demanding conditions to be expected. That is not an original line from me. I will get to the author shortly. In terms of the philosophy of design requirements, I think Mr. Levett and I are on the same page here. We firmly believe that the design requirements should be performance-based and not prescriptive. Obviously, prescriptive regulations are inherently limiting in terms of the technology and innovation. And of course, they often lag the technology because it's tough to change a prescriptive regulation. They're always slow to update. And obviously, as the conditions the regulations are supposed to address change, again, the regulations are unlikely to pick up. And as I mentioned earlier, they've got to address at least the times we failed. It would be nice to win the next war, but at least make sure we can win the last ones we lost. But the real key to any new design regulation is testing. I once had a colleague, in fact, Dr. John Shine, who invented maraging steel, who once remarked that one test is worth 1,000 expert opinions. And that is a good dictum. If these things are going to be expected to work under conditions where all hell is breaking loose, they've got to be tested in conditions that simulate all hell breaking loose. Now, I recognize, and we at the Academy recognize, that's neither cheap nor easy, but neither is cleaning up 5 million barrels of oil. So the consequences of not doing these tests under very difficult conditions have got to be weighed against the consequences of failing to operate under very difficult conditions. Now, this, in the immortal words of Yogi Berra, deja vu all over again, this study done for West Engineering for MMS in 2002 was, can a given rig BOP shear the pipe used in a given drilling program at the most demanding conditions to be expected? Now, this is 10 years ago. These words were uttered. And of course, they concluded 10 years ago that the limited data set from the last generation, grim picture, those are not my words, those were words provided to MMS 10 years ago by a contractor asked to look at this specific topic. And even more recently, we've had studies of BOP reliability that I believe have been flawed because of the inclusion of hours and hours and hours and activations under the most benign conditions that, sure, they're great for the eyewash on the reliability number, but they do nothing to tell us about what the performance is going to be under the really difficult conditions. So hours of use data are not the way to go here. West Engineering, this is again their graphic, used with permission, I might ask, indicating the results of their testing 10 years ago. Now, if we didn't listen then, we got to make sure not to repeat that question now. So I hate to disagree with my moderator, Professor Sears, but I don't think, certainly I was not under the impression these things were robust and reliable. This was my picture of the reliability of BOPs. Now, to my knowledge, if someone did some testing to contradict this, I didn't see this. That doesn't mean it wasn't done, but I'm unaware of it. So I don't think there was a perception. I think the greater perception, and this is just me personally, was that we're never going to need them anyway, and so why spend a lot of money making them even more expensive? Well, in point of fact, the unthinkable did happen, and now it's very thinkable. And obviously, we've got to revisit the worst engineering conditions. Those West Engineering tests we just saw for that graphic from were static, no dynamics considered. They were conducted on drill strings centered in the BSR and in tension. They were conducted under ambient conditions corrected for pressure. I'm not critical of the correction. Yet a 50% failure rate under these conditions was observed. Now, if we do the test and they tell us we got a problem and we walk away from it, we are going to have a problem again. Obviously, under the new regulations, any test failure, or we've talked a lot about monitoring, but monitoring has got to have consequences. When, if it's going to mean anything. If situational monitoring, the BOP, indicates that piece of hardware is unavailable or has a problem, drilling has to stop. That will do wonders in and of itself for the reliability, trust me. Now, more recently, the API RP53 has presented it to then BOM a GIP study, and note the date of this presentation, September 13th. This is 4 months after Macondo, and yet if you look down at the BSR, we have a equipment probability of success. By the way, that's not my graphic, that's their graphic, 99.5%. Come on. Now, at the time West did its tests, it was unaware of any regulatory requirements that the BOP must be capable of shearing the pipe in front of it. Obviously, that needs to be cured. Obviously, there's been no redundancy. One BSR, one shuttle valve, MUX cables independently. Obviously, the biggest single shortcoming is pipes and compression, and not to mention not being able to handle all sorts of pipes that may be in front of it. And as previous speakers have identified, a perfectly designed BOP can be useless if operators don't understand or know where to use it. And they can't be expected under high stress situations to make a complex decision. And it should be added that, remember, the Macondo well, if you believe 50,000 barrels a day, is a 3.4 gigawatt power line. Yet, the crew sat there for 7 minutes before they punched the button and let 3.4 gigawatts assault their vessel. Now, think about the design requirement if any of these designs have to take 3.4 gigawatts of insult for 7 minutes before the activation is given. That is a terrible design problem. I think we have to get rid of that 3.4 gigawatt requirement. And so the expert systems have to be there to help people out and do what's required. If you looked at the Transocean procedure in place at the time, and I'm not critical of this per se, but this is what they were supposed to do in the middle of an emergency. And obviously, for the reasons that people indicated, they didn't know the condition of the valves, the solenoids, the flow velocity, as many have identified. And the fact that there were faults in the BOP system didn't cause drilling operations to cease. And obviously, most of the current shear rams in use will not seal if the pipe is in compression today. Learning about tubes or pipes in compression and not sealing in BOPs is not new news. We've heard that, we've now known that for 10 years. So the recommendations here are just those in the NAE report, and you can read them for yourself. The lesson we have to take away with this is obviously the systems that failed on the BOP that day made the difference between what should have been just a kick instead of an horrendous national accident. And in the immortal words of Santayana, if we don't remember this past, we are condemned to repeat it. Thank you.
Thanks very much, Roger. The next speaker in this panel is Frank Gallander. Frank, and this is really a nice transition because the first two speakers now we've seen a lot of what should be done, and the next two speakers are going to talk about what is being done. Frank has a long career, 36 years in this industry, 31 years with Chevron. He's currently intervention consultant for Chevron Upstream, involved in oil and gas drilling and completion operations. And he's very significantly right now chairman of API Standard 53 and is going to talk to us about API Standard Recommended Practice 53.
Thank you, Mr. Sears. I'd like to thank the director for hosting this and giving us the opportunity to be here today. I'd like to give you kind of an update on where we are with Standard 53 and where we plan to be going ahead here in the next couple of months. The standard is the industry document, guidance document, I should say, for the operation and maintenance of drilling BOP equipment. Post-Macondo, when we took on the task, we looked at the old document, the RP 53 as it was written, and there was 21 sections in it. We looked at the 21 sections and we knew that there were other documents out there that existed that this was in direct conflict with. So we went through the document and did kind of a clean cut on what was covered in other documentation that did not require to be addressed in an operations and maintenance type guidance document. So we took those out. We narrowed it down to 7 sections. The first 5 sections is common to both the surface and subsea BOP. It's common to both, so there's no big distinct difference. The section 6 is assigned specifically to surface BOP and control systems and how you maintain and operate them. Section 7 goes more in depth into the subsea side of it. We also took the opportunity to incorporate some of the effects of negative pressure on the subsea BOPs. We'd never done that before, but this was an opportunity to look at it, so we incorporated those into the document. We identified condition-based maintenance as an alternative to schedule-based maintenance. Previously, all the API documents, specifically 53, really focus on schedule-based maintenance. We looked at it and said, well, there's an opportunity here because we're looking at differences in technology, differences in equipment, so we threw in the opportunity for a person to select whether it's going to be condition-based or whether it's going to be schedule-based. Included additional verbiage, language on competency, training, procedures, and such. And most importantly, in my view, was the change from an RP to a standard. There's more greater emphasis between the equipment manufacturers and the equipment owners, as exhibited in the annex that gives direct instructions on the communications route for the manufacturer and the equipment owner. There are some prescriptive points in the document, specifically the drawdown test, which refers back to specification 16D, and that specification is for the design, manufacturing, and testing of BOP control systems. In the verbiage, you'll notice that there's specific requirements that you have to perform and results from the test. One of the other things we did is we looked at all the various API documents, and we looked at how others in the industry were using a BOP and how it was identified. So we regrouped and said, okay, first of all, let's define what a BOP is. So we looked at all the documents, we put it together. So we came up with this definition of a BOP, And subsequently, after going through the other documents, we reserved back to say, okay, let's explain what a BOP isn't. So looking at other documents, we took out of the other documents and we defined that a BOP is not a gate valve, it's not a workover control package, it's not a subsea shut-in device, it's not a well control components, that's as per RP 16ST, which is specific to coiled tubing operations. That's what they refer to their well control system as opposed to a BOP. Intervention control packages, diverters, rotating heads, circulating devices, cap and stacks, snubbing units, stripping units, et cetera. So we kind of broke that apart to say, if you're going to build a BOP, this is what it's got to meet. And this is how you're going to operate it, and this is how you will maintain it. Additionally, we took in consideration the RP 96, which is the guiding document for the design and construction of deepwater subsea wells. The definition that they had developed would also play part in the way that we used our document. So we took MASP and put it in as a design load that represents the maximum pressure that may occur at the surface during well construction or production. Additionally, as part of a subsea well, you would have to look at the MAWHP, which is the MOT, and the definition there is the highest pressure predicted to be encountered at the wellhead in a subsea well. Now, this number can be identified in each hole section as well as the full breadth of the well. So during the write of the document, we continued checking over our shoulder at other API documents and other committee discussions that were going on to try to have some level of consistency in the messages that we were writing and the documents we were producing. There's one new additional definition that comes into place, and this is the maximum expected wellhead shear pressure, which I think kind of meets some of the discussions that we've seen so far. And that is the expected pressure at the wellhead for a given hole condition or a given hole section, a specific shear pressure requirement, specific operating piston design, the drill pipe material specifications, to achieve shearing at mass, MOP, or whatever other pressure limiting design value that you have for the well. In addition, there's other points that's included into this section in service and subsea that give you more discussion points and considerations pertaining to dealing with the MEWSP. Sorry. Early on in the discussions, we knew that we were going to get into some areas where we would agree to disagree and move on. To address that, we had to prioritize two items that would be our governing words. So of the two words we came up with, we all agreed that when we came to an impasse, life and the environment would take precedent. Everything else in the discussion followed. So those two would help us get past an impasse. We updated the tables for testing, including the frequency and acceptance criteria. And we also used the clarification of the use of fire retardant or gas permeating hoses for control systems, which is 16D, or 16C, which is choke and kill systems. So in this case, lines where hydrocarbons can be introduced and permeate through the line structure are required to meet API spec 16C fire testing requirements. Those lines that are incapable of getting hydrocarbons introduced are not required to meet the fire requirements of 16C. We put that specific language in there because, once again, we didn't say this prescriptive as much as trying to be clear in the intent of what we wanted to document. Additional testing requirements have been put in. Just one example of it is we added the riser recoil system, which we haven't done in the past, but now it's included into it, and there are others as well. We took in consideration the Joint Industry Task Force equipment recommendations that came to us post-Macondo. The ROV interface standardization has been adopted. It's now an industry standard for it, and we also adopted the minimum functions that are going to be required to hold the ROV interface configuration. We also included requirements for 20, 25, and 30K systems, defined BOP classifications with regard to well-controlled equipment, with some relationship given to the pressure. And again, we considered all the past JIPs and other JITFs that recommendations that had come to API. They passed them on to us for also inclusion into the document. The last document, we received 281 comments. Approximately 40% of those were technical in nature. We've addressed those. We had the last meeting for the task group on May 18th, last Friday, with the intent of going through and resolving all the comments from the second ballot. Our intent now is to go out in June with another ballot for review, about a 2-week session. So that'll happen in June, and hopefully we will have a summer document come out that's finalized and hopefully issued by early fall. That's the intent, and that's where we're at right now.
The fourth speaker this morning in this panel is Chuck Chauviere. Chuck is General Manager of Drilling for GE Oil and Gas, has a long career in the industry with equipment manufacturers, and so this is a way to bring this panel around and ground us in the real world of actually building these systems that have to operate in the ways that have been described so far. Chuck currently with GE Oil and Gas, previously with Hydril and Cameron, and brings that experience and the perspectives of GE to this discussion. Thank you, Chuck.
Thank you all very much. So as a manufacturer, you know, we're born by many challenges on what to do and how to do. And so as being part of this panel, it's an interesting challenge that we all face. And so in stepping through some of these things, I am going to step back a little bit, sort of give an overall view, but then I'm also going to give some examples of what a healthy industry does, which I believe we have, where we share information back and forth, and to the point of many of the speakers, where we provide those learnings and we embed those back as part of a journey, a long design journey. Being part of a company that has been in the BOP business for 80 years, we recognize as we move from land to offshore to subsea to deep water, this is an evolutionary process. Now, you know, any of the things we're looking at right now aren't extraordinarily revolutionary, but we need to recognize there's a way to roll those out. So I'm going to show you some things and then we'll step through it. Now, this is, as we talked about, what this panel is trying to accomplish. And one of the things I wanted to highlight up here is, for instance, this concept of cut and seal. And I want to make sure, as we're talking about giving these design parameters to engineers, we got lots of engineers in here. Engineers say, what do you want? And then they want to go do it. And so we need to be careful that if we put phrases like cut and seal, they're going to go try to accomplish it by cutting and sealing. I'm here to say, tell them what you want, which is stop it. Whatever it is, you want to stop it. Now, if that requires it to be cut and seal in the same cavity, then so be it. If you cut in one and seal in the other, I don't think anybody in this group is really affected by that. You just want it to happen. So that's one of the things. Now, I wanted to highlight, this is this concept of foreseeable. As we get all the information and we get the forensic knowledge, I think that's very valuable as an OEM, because those are things that we can respond and react to. This concept of foreseeable, you know, we use phrases like any and all. That's not something that we can convert to tangible action. I think we all recognize what the challenge is, but we just need to make sure we're working through that so that we're using reasonable thought processes around this entire ecosystem that we work in. Now, I don't know why I moved it around. Look, the ecosystem that we're in, we recognize we have a very diverse crowd. We have many different stakeholders. This isn't something that's trying to identify all those stakeholders, but we recognize from the regulations, the regulatory bodies, the individuals that do things, the equipment provider, the users, you know, and the information that you use. This is a large ecosystem that we're working in, And it's something that we need to continue to collaborate on, because I think the majority of us know we're not talking about thousands of these things. These aren't thousands of deep water drilling systems out there. These are in the hundreds. So we recognize it has to be a collaborative approach. We can't put the burden on any one organization or set of groups to do this. This is something that is going to take many, many people and bodies to work on, because we recognize from the aspect of developing technology, this is our license to operate for all of us. So if it's our license to operate, then we need to do it appropriately. And to the point of some of the other speakers, this is for a global activity. These are mobile offshore drilling units. They don't just sit in the Gulf of Mexico, they move around the world. So we recognize we need to satisfy many, many stakeholders and regions. Now, I put this one up here just to get everybody sort of calibrated to the complex dynamics that happen below the ocean. So we are focusing just on this element over here. Now, this is a BOP system on a horizontal tree. So this is after all drilling is done that the system shows up. So let's make sure when we're talking about what passes through it, what it has to do, what are the multitude of possibilities, that we address all these things and that we don't just get so myopic in our views. So there are many, many challenges out there. As part of the design, as we're looking at this, pressures are getting greater. As it gets deeper, the external pressures get greater, the internal pressures get greater. We even get negative pressures internal to the system. So there are many challenges we need to work through. Temperatures. We hear things of high temperature wells. Different initiatives are in place for that. This affects metallurgy, it affects fatigue, it affects the elastomer. We have got to make sure that we do elaborate on what this needs to look like, from going completely cold at seafloor conditions to completely whatever the hot is. And hot's an interesting dynamic in this industry. This is my best graphic I found for forces. So look, we have compression, we have tension that have been talked about, you have bending, you have torsion. These things are under unbelievable loads. When you think about the loads that they see, you have got to include all of those things. These design parameters are important to the industry, and we respond to them as they are given to us. Now, this is the other thing about what are the environmental test data. Now, when you talk about testing under internal flows and what those flows may or may not look like, and exactly how you replicate and model those flows, this is a big deal. Again, there's external conditions and internal conditions that we need to work through, and that is a challenge for the industry. The industry has done testing under certain types of conditions, but in this all hell breaks loose scenario, we've got some work in front of us, and we need to work on that. Now, finally, the speed of decision making. This is something that we continue to talk about, which is, how does this work? Now, we also have the speed of technology and adoption and grandfathering, all those other things, but the speed and the accuracy of the data to enable this. We are still dependent, and we talked about it, about an individual knowing when to push the EDS. That is critically important to us because, as we've talked about, there's many factors that impact that. Now, I've got a thing in here that'll show what an EDS is. Hopefully, for those of you that are working it, you know what a typical EDS sequence does and why it exists the way it does exist. Now, again, we're just talking about tools of the trade. These are tools of the trade that are used by people with procedures, with control processes in place, and we recognize there are different tools for different applications, and you have to know what the tool is capable of doing when you're using the tool. That being said, there are multiple tools that we use in the industry. We have the example of the annular blowout preventer, which has different functions that it serves, and we've been really focusing on the ram blowout preventer and specifically the shearing element of it. And so I'll show you some of those things in just a second. Last thing, not last thing on this topic, but quickly moving through, this is just an example of things where you say it is very factual that people want the right thing. This is just the evolution of airbags and seat belts in the automotive industry. We're talking about how do you short cycle this and bring something to market really quick, which means we have to do something unique in the industry. Now, I'm going to try to show, this is a thing where I showed the concept of we have a few things that we have worked on based on some of the learnings that we've got from the field. Hopefully this will run. Uh-oh. Good grief. Stand by. All right, so this is just things that you can do with the equipment. I'll talk through it a little bit, but this is about how can you utilize the assets best in the field. As we got feedback from the industry, we realized that you need to have equipment that is very usable in many different applications. So this is a little bit of a containment or a response scenario. This is between an LMRP and the BOP stack. This just shows an example of a disconnect, leaving the stack behind, and then coming with a different vessel with an interchangeable lower marine riser package that you can then bring alongside to engage that system. I'll let it roll, and I know I'm compressing for time. Hopefully you get the concept that the industry is providing solutions that will enable us for this license to operate. Now, quickly, we talked about data. This is an ROV data display package. This is for a stack that has no power, no controls, where you can visually see the pressure, the temperature in the bore, the position of the rams, and you can get a variety of that information without having any surface control. So again, this is technology that we have out there. The last video I'm going to show you, and this is very germane to cut and seal. This was at our Offshore Technology Conference. This year we showed this. I'm going to show you a video. I will talk through it, and then I promise I will be done. So what you're going to see, this is going to be a shear test that we have done. And this is on a pipe that is in a buckled situation. And there's a number of conditions that will show on this. You folks can read it, and then I'll highlight what you're looking at. It's a short video, I promise. It's a minute and a half. Okay, so what you're looking at in this side here, this is a pipe, and we're going to begin to buckle the pipe. The pipe is now hard over to the side, and then we're going to engage the new shear blades that we have that fit in existing cavities. The point here is the system is hard over. The pipe collects it into the shear plane. You'll see it bring it over. At that point, it brings it in. Now, this is an offset in tension or in compression shear. So it is showing that the industry responds to forensic information that's given to us. This is something that we need to continue to encourage and engage in the industry as part of these committees. This one is just, now we understand we play globally. This was a requirement for a different operator to shear in a region. Now this is then shearing an actual tool joint. This used to be considered an unshearable. With this new device, we're able to cut and seal tool joints. Now, it's not everything that we can cut and seal, but we're improving what the capabilities of the equipment are. With that, I'll stop, and I apologize for running over. Thank you all.
Thank you, Jeff. Okay, we do have a few minutes for questions from the audience.
Hi, Holly Hopkins with API. Frank, would you like to clarify for us the joint industry project slide that was in Mr. McCarthy's presentation and the changes to 53 that have made in response to that project? Would you like to clarify the JIP slide that was in Mr. McCarthy's presentation, including the improvements that have been done to 53 to address that?
The presentation that Dr. McCarthy showed was the presentation we gave to Director Bromwich in September, and that was when Bromwich was still director at the time. And that was just kind of an update to him as to what have we been doing and what was going on. The study that, another part of the study at the time, or the discussion, was about going back to work. And so we left it kind of, this is just the studies that were done, that we just completed just prior to the McCarthy incident.
Okay.
I wanted to ask Dr. McCarthy, the intent, the slide you showed about the West and the one from the director that I gave, what was the intent of your discussion point?
The discussion point is, I guess I didn't make clear, I was trying to make clear, is that the industry had plenty of warning about the problems of shearing even pipe they were designed for under very benign conditions as set forth by West. Yet, somehow, for reasons I don't understand, instead of concentrating, which I think West did properly, did at the time, on actual testing of shearing and conditions, somehow the industry started looking at, okay, how many hours were they out there and how many times were they activated and how many times they worked? Well, that makes a great reliability nothing, but it doesn't tell us anything about when all hell breaks loose. So I was contrasting those two different approaches. When West did the tests, they failed. But when you just add up a whole bunch of operational hours when things are calm and nothing's going on, you can get some really high reliability numbers that tell you nothing about your emergency performance.
I think there's another question. Yep.
Gutierrez, Director of Technology Innovation for Transocean. I appreciate the panelists for providing the framework and context for this discussion. One thing that I think we all agree is the performance. We need to make this new regulatory framework based on performance. And that brings me to the point of metrics. We need somehow, before defining what are the regulatory space or the new space, what are the metrics that we need to pursue? And one that really don't have something to propose yet, but I definitely think we need to put our brains on is how to eliminate the issue of the man-in-the-middle control. We have a very complex control system, and yet we are relying on that button. And how you model pushing that button in that case of panic and chaos. So I just hear your comment on what do you think we need to be arguing and discussing about. Thank you.
What we need to establish first is what exactly do we want the performance to be? And I think that's still an issue that needs to be discussed and agreed upon, because again, it becomes a matter of what side of the bow tie do you expect this to work on? And as Roger was mentioning, when you're talking about the situation with all hell breaks loose, there's a lot of us in the industry that understand that emergency disconnect was not necessarily originally thought of as something you needed to do for all hell breaks loose at the wellhead. It was all hell breaks loose up at the surface when all of a sudden the rig just decides it wants to go somewhere else and you no longer are connected to the well. So it was intended to be a way to safely shut that well in. And the expectation was we still had primary well control in place, but we were about to lose our connection and we needed to make sure we were secure. Now we're talking about a completely different circumstance. And so first of all, let's agree, what do we want this to do? And if we don't think a BOP is capable of being developed to a point where it can handle all hell breaks loose, let's come up with a different innovation that will handle all hell breaks loose and figure out how all of that's added together. That to me is the first and foremost primary challenge, to define what that performance needs to be, and then we can decide what metrics we want to have for that performance.
I think Chuck made a very good point. You know, at the end of the day, engineers who design BOPs have to be given specific performance metrics. I mean, we just can't, we can only talk in generalities for so long. And that's why this is an important topic at a design requirements conference, because when you're talking about a design requirement, that's going to set forth the testing requirements that it has to pass to be a certified design. And so these generalities that we've been talking about today have to be translated into specific pressures, flows, temperatures, shocks that the iron has got to meet. And I don't mean to minimize the technical challenge of that process, but it can be done, and it needs to be done, because the consequences of not doing it are just too great. So we've got that challenge ahead of us, no question, and we're going to have to come up with some standardized tests that do our best to replicate the last war, which we lost.
Okay, thank you, everybody. That brings this panel to a